And then Rutherford came along, and Rutherford did his famous experiment when he was at the Cavendish in England, where he took a very thin sheet of gold foil. You know, you can make gold really thin, like gold leaf, yeah, really thin. And then he shot at it these newfangled things called alpha particles, you know, from a radioactive decay, which had very recently been discovered as well, and indeed Rutherford was involved in that heavily. He shot some alpha particles at this sheet of gold foil, and what he found is that, see, if it was plum pudding model, and you have all these little plum puddings stuck together like they would be on the shelves at the supermarket, then you would expect these big, so alpha particles are quite big things, they would hit them and bounce back. Yeah? Because how would they go through? There's no space, because all these atoms are stuck together. What he found was that the vast majority of the alpha particles went straight through. Some of them bounced straight back, some of them bounced back at an angle, but by and large they all went straight through. And so what that meant was that the vast majority of the atom must be empty space if the alpha particles can go straight through. And so this led Rutherford to propose what we now kind of accept to be the way that an atom is put together. And it should be pointed out he would never won a Nobel Prize for this. Yeah? He was the guy who said atoms are built like little baby solar systems, you know, one of the iconic images of science and of chemistry, and he never got a Nobel Prize for that. Never mind. And so here's the idea of the atom as we have it now. We have a central piece in the middle called a nucleus, and that's where the protons are. It's also where something called neutrons are. Neutrons were discovered a little bit later, but the protons and the neutrons, which are the big parts of the atom, the big, massive, the ones with the biggest mass, they live in the middle called the nucleus. The electrons, the negatively charged bits, don't live in the nucleus, but instead they circle around the outside. Right? And so in its first incarnation, it was kind of like the solar system, where the nucleus is the sun, and the electrons are like the planets going around. As we'll see, it's actually a bit more complicated than that. But you can think about that in the first instance, right? And so in the same way that you have comets and stuff that come through the solar system and out the other side without hitting anything, that was like the alpha particles in Rutherford's experiment. They came through and out the other side, never hit anything, because most of the atom is in fact empty space. About 99% of the atom is empty space. In fact, it's more than that, I think. There's various different pictures that people have proposed. That you can have things like, if you imagine, someone said Westminster Abbey. Has anyone been to Westminster Abbey? There you go, some people. It was on that movie, that King's Speech thing I saw last night. Yeah. So if you're not sure, it's a huge big cathedral. Imagine a bumblebee flying around inside there. So the bumblebee, so if the volume of Westminster Abbey is the volume of the atom, then the nucleus is like the bumblebees flying around in the middle. So all the rest of it's just empty space except for where the electrons are zipping around. Right? The electrons are really small though. They're only about 1/2000th of the size of a proton or a neutron. So they're really tiny anyway, and they're zipping around, and most of it's just empty space. So what that means is that 99% of you is empty space. And 99% of that is empty space. And 99% of everything is empty space. Yeah? So that's interesting. Maybe slightly disturbing, but interesting. As the years have gone on, this picture of the atom has become more refined, in particular the way that the electrons are arranged around the nucleus. And we're going to come back to how that works shortly. We've got one more slide and then we're going to move away from the nucleus. So what I said was that the protons and the neutrons are the very big things. And so if we want to talk about the mass of an atom, then we're talking about the mass of the protons and the neutrons put together. The mass of the electron doesn't really matter because it's really, really tiny. Yeah? If we come back to our periodic table then you will see that each of the boxes represents a different atom, and each of those boxes has two numbers in it. And in pretty much every periodic table you see will be like this. The number at the top is this thing called the atomic number, and this tells you about how many protons there are in the nucleus of your atom. So if you're hydrogen, then the number in there is a 1, and that means that a hydrogen atom has one proton. And indeed, this is how we define the atom. This is how we know it's an atom of hydrogen. It's not to do with the number of neutrons, and it's not to do with the number of electrons, it's to do with the number of protons. Right? So anytime you have an atom which has one proton on it, it's a hydrogen of some flavor or other. In the same way, if you look at cesium, cesium has a 55 above it, that means a cesium atom has 55 protons in it. Or an iodine over there is 53, so an iodine atom has 53 protons in it, and so on and so on. So the number of protons is what defines a particular atom to be a particular type, right? So a hydrogen always has one proton. If you are a so-called neutral atom, then the atomic number will also tell you the number of electrons in your atom, right? Because remember, the protons are positively charged and the electrons are negatively charged, and so in a neutral atom, i.e. one that has no overall charge, then the number of protons and the number of electrons must be the same. So those charges cancel out. Yeah? The neutrons don't matter because the neutrons are neutral. That's why they're called that. So they have no charge, so that doesn't have a bearing on this. But if you're a neutral atom, then the number of protons and the number of electrons will be the same. The other number that you find in each of the boxes in the periodic table is something called the relative atomic mass. And so this number is talking about how big the atom is in terms of how big. How much stuff there is in the nucleus. There you go. So we can define the relative atomic number as being the number of protons plus the number of neutrons. Now obviously this isn't the actual mass. The actual mass of a hydrogen atom is something like 2 times 10 to the negative 26 kilograms. Right? It's a little number. That's not these numbers. What these are is a relative atomic mass. So relative to some other element in the periodic table. It turns out that it's all relative to carbon. Right? So carbon, as we're going to see in a bit, is defined to be 12. It's actually 12.01, but we'll get to that. And so the fact that the hydrogen is given a 1 just means that it's 1/12 the mass of a carbon. Yeah? So if we then have these two numbers, we know that the atomic number is 1, and we know that the relative atomic mass is, in the case of, well, let's look at oxygen. That's probably better for the moment. Oxygen has an atomic number of 8 and a relative atomic mass of 16. Then what that tells you is that because the atomic number is 8, it has 8 protons and it has 8 electrons. Because the relative atomic mass is 16, that means that there must also be 8 neutrons. Yeah? Because that number has to be the number of protons plus the number of neutrons, and we know that it's got 8 protons because its atomic number is 8, so then the number of neutrons must be 8 as well to add up to 16. Does that make sense? Yeah? Okay. So, then the next obvious question is, well, why is hydrogen 1.008? Why isn't it 1 or 2? Can you have little pieces of neutron in there as well to make the mass up to that? The answer is no. You can divide neutrons into pieces, but that's physics, not chemistry. Yeah? That's quarks and stuff. We don't do that here. The reason why those numbers aren't always whole numbers is because you can get different types of the same atom which have different numbers of neutrons in them. And so these are called isotopes. And so we can say that an isotope is where you have atoms of the same element, so in other words the same number of protons, the same atomic number, but with different numbers of neutrons. And so the classic example that we always give is chlorine. So if you look up chlorine on a periodic table, you'll find that its mass is 35.45. Right? And that's because there are mostly two types of chlorine atoms in the universe. One of them has a relative atomic mass of 35, and one has a relative atomic mass of 37. Right? So see, we write them like this, a little 35 up here and then the Cl, and a 37 up here and a Cl. Right? So these numbers, when they're written this way, this refers to the relative atomic mass. We know it's chlorine, so that means the number of protons must be 17. If it wasn't 17, it wouldn't be chlorine. It would be something else. Yeah? If these are neutral atoms, then the number of electrons must also be 17, because they have to be the same as the number of protons, so that the negative charges cancel out with all the positive charges. Yeah? But then if we use our little formula, if you like, to work out if you've got a total mass of 35 and you've got 17 protons, that must mean that there's 18 neutrons in this particular type of chlorine, 17 protons and 18 neutrons to add up to 35. Whereas for this one, the 37 chlorine, if you've got 17 protons, you must have 20 neutrons to add up to a total mass of 37. Yeah? And so these are two different types of chlorine. And often what you find is that one, you get isotopes which are unstable and other isotopes which are stable. And this is this whole thing about 235 uranium versus 238 uranium. And 235 is the radioactive one. It's unstable. They're both uranium, but one's different to the other because it's got a different number of neutrons in its nucleus. Yeah? So you have these two different types, and then, to make things slightly more complicated, you find that they have different abundances. So about 3/4 of all the chlorine atoms in the universe are this one, and about 1/4 of all the chlorine atoms in the universe are this one. And so to work out the atomic mass, or the relative atomic mass, what we do is we just take a weighted average. Right? So it's the 35 times that 75.8% plus 37 times 24.2%, all divided by 100. And so if you like, the average mass of all the chlorine atoms in the universe is about 35.5. Yeah? You see how that works? So don't be thrown by the fact that in most cases these numbers are not whole numbers. I mean, if you look at the table up there, far and away it's more common that the relative atomic mass is not a whole number. A lot of them are very close. Like gold is what, 196.9665 or something, if I can read that. So it's pretty close to a whole number, but not quite. Because pretty much all atoms have these different possibilities based on how many neutrons they've got. Okay? And so these are called isotopes.